Alright, so Chapter 6, Differential Equations and Mathematical Modeling. Section 1 is Antiderivatives and Slope Fields. So we kind of started this off a little bit. I do want to fix a few things. An equation containing a derivative like this, dy dx equals y ln of x, is called a differential equation. The initial value problems are problems in which we are trying to find the function. So we're given the derivative and we want to find the antiderivative, aka the integral, and a point, a f of a. So that's an initial value problem. You're given the initial value, so that way you can solve for c. And we kind of did an example in class. The value of f for one value of x, in this case a f of a, is called the initial condition. So this helps us solve for c. This right here is called the initial condition, okay? But the whole problem itself is called initial value problem. So when we find all the functions of y that satisfy the differential equation, we have solved the differential equation. When we find the particular solution that fulfills the initial condition, we have solved the initial value problem, including c. Alright, now this first problem, it's kind of taking us back a little bit to last year when we had to do related rates. So let's read this, and as I'm reading, I'm going to be writing on the side what I'm getting from this. So I'll write circular cylindrical tank. Okay? So I'll write circular cylindrical tank with a radius of 5 and a height of 16 feet that was initially full of water is being drained. So initially it was full of water and is being drained at a rate, so that means that our dv dt, right, if you guys remember, our dv dt is 0.5 times square root of x feet cubed. So because it's feet cubed, I know that it's going to be volume and not area. That's what tells me that it's volume. Okay? Find a formula for the depth and the amount of water in the tank at time t. How long will it take to empty the tank? So step 1, we have to find the formula for depth. So we have to find x of t equals what? Step 2, we have to find the volume formula. And then the last part says how long will it take for the tank to be empty? So that means basically when x is 0. So this is telling us t is what when x is 0. That means when there is no water left. Now Torricelli's law is a law that says if you drain a tank, the rate at which the water runs out is a constant times the square root of the water's depth x. So when the water runs out is a constant times, so it's a constant, times the square root of the water's depth, aka x. The constant depends on the size of the exit valve. And when they say that, it's kind of, this is how you have to think about it. If you have your right circular cylinder tank, this is what they mean. So if you have water in here, and here is your exit valve, then depending on the size of this, will determine our constant. Now we already have our constant in this problem. Okay, it's 0.5. So Torricelli's law specifically deals with this type of problem. It's a problem about draining a tank depending on the size of the valve. And they tell us basically the size of the valve here is 0.5. Now this problem is kind of long, So I'm going to start it off, and we'll see how far we can get. So if you remember, they gave us dv dt, correct? They gave us dv dt, which is 0.5 square root of x feet cubed per minute. They also gave us our height. Now they gave us the height of the tank, which is 16, but really the height of the water right now, that's what we're trying to solve. So our height is going to become our unknown because we are figuring out how high the water is at different time intervals. Okay? And then they did tell us that R is 5 and R is constant. So it will never change, correct? So that means dr dt, the rate of R is going to be 0. Now here h is not constant, it is changing because h depends on the water. So the height of the water is changing. Okay? So knowing this and knowing that it's a volume problem, I'm going to set up my volume problem. Remember, from related rates, you know that this is volume. So first you have to set up pi r squared times x. Now, I know that r is constant, so this is just going to be pi times 5 squared times x, which gives us a volume of 25 pi x. So what this is saying is that as we drain the tank, the height changes with time according to Torricelli's law, right? So the height is changing. So that's why I cannot consider this to be a constant. So as the height changes, so does the volume. This is what this is saying. So as height changes, so does the volume. So knowing that these two are going to be changing, their rates are going to be changing, right? As this thing goes down, so does the volume. If volume goes down, so does the height of the water. And of course, this is with respect to time. So what do we have to do when we have two different things that are related to each other? This is called a related rates problem. So if you remember, what do? We're going to differentiate both sides with respect to time. So basically v prime, take this prime of that, and 25 pi x prime. Alright, remember that this is just a number times x. So the derivative of v prime is dv dt, and the derivative of 25 pi x is just going to be 25 pi times dx dt. So even if we waited to plug in the r until we got to this point, that still would have worked, but it makes it easier doing this. Okay, so now we know what dv dt is. That was given to us. It's 0.5 times square root of x, and that equals 25 pi dx dt. We want to group things together. We want to group the x's, the dx's, the t's, and dt's if possible. Why? Because we want x of t, right? We want x by itself. So basically the idea is I want to get this guy by itself, if possible. Actually, I'm sorry. The x's together, and then the dt by itself. So I want to group the x's and the dt's separately. So first thing I'm going to do is I'm going to move over this 0.5. So this becomes square root of x equals 25 divided by 0.5, which is just 50 pi dx dt. If I multiply both sides by dt, and you'll see why in a second why we need to do this, that cancels out and we end up with dt square root of x equals 50 pi dx. I still want my x's together. Okay, so I'm going to divide both sides by dx. I'm sorry, by square root of x. Square root of x. So now I got dt equals 50 pi dx over square root of x. And then I can move that 50 pi over. It really doesn't matter. I think you're still going to end up with the same exact looking problem, but that way we are keeping the x's all by themselves. Okay? So I'm going to divide both sides by 50 pi, so we get dt over 50 pi equals dx over square root of x. Now, since this is the derivative, okay, and this is the derivative, what we're going to do is we're going to integrate or find the antiderivative both sides. So we're going to integrate this and we're going to integrate that. So what this looks like is it's the integral of 1 over 50 pi dt. Does that make more sense now that you see it like this? Over 1 over square root of x dx. Now it's easy to integrate because the x belongs, it's with respect to x, and this is with respect to t. Okay? So, integrating this, because technically this is one problem and we are separating the integral, we are going to make a super constant. And I'm going to explain what that means in just a second. Because technically this is all one equation. So really there's only going to be one c, right? Only one c. So I can't put a c here and a c here. I'm going to pick one of the sides and that is going to be where my c is going to go. Because these are not separate integrals. This is still part of a big equation. So when we integrate this, this is going to become 1 over 50 pi t, because this is with respect to t, equals, remember that this is x to the negative 1/2, so integrating it gives us x to the 1/2 over 1/2 plus c. That's going to be my super constant. I'm only putting it on this side. Now something I lost track of right at the beginning is the rate. The rate up here has to be negative. Why? Because it is decreasing. So I kind of have to go through and make sure that that is put back into my problem, which makes this guy a negative, and that a negative, and that a negative, and that a negative. This is going to be negative. Therefore, this is going to be negative. Sorry about that. Okay? So because the water is decreasing, the rate is going to be negative. Okay? And now, basically, we have our problem. Okay? It's negative 1 over 50 pi times t equals equals 2x to the 1/2 plus c, my super constant. So what were our initial conditions? Let's apply our initial conditions, which means before the drain started to empty, how much water did we have? It said it was full, right? So basically, when time was 0, before it started to empty, our x, our height, was 16. So we're going to use our initial conditions in our problem to solve for C. So we're going to apply our initial conditions to solve for C. So I'm going to come back up here. I'm just going to draw a line. So now I'm going to take my problem, -1 over 50 pi times 0. I'm applying my initial conditions equals 2 times 16 to the 1/2 plus C. Solve this. This is 0 equals 2 times 4 plus C. So 0 equals 8 plus C. -8 equals C. So there's my C. So we're going to plug this back in to our problem. And we get -150 pi t equals 2x to the 1/2 minus 8. So to solve for x of t, we're going to get x by itself. So move everything over to get x by itself. So I'm going to add 8, and then I'm going to divide by 2, and then I'm going to take the square of both sides. So we end up with -150 pi t plus 8. I'm going to divide everything by 2, and then I'm going to square it all. Now that is an ugly way of looking at it, of course, but when you clean this up, this will end up being, flip the guy and multiply for this one, right? So this is going to be -1 over 100 pi t plus 4 squared equals x, which is the same thing as saying x of t. Okay? So that's the answer for the depth. So if I wanted to figure out the depth at any time, this is the equation that I would use. If I wanted to figure out the depth of the water after 5 seconds of letting water run out, I just plug in, or 5 minutes, sorry, I just plug in 5 minutes and I figure out where my depth is. Now the last thing it said, when is the tank empty? So find t when x is 0, when the tank is empty, when the height is 0. So you can use this equation, and you're solving for t here, except x is going to be 0. So after you solve it, right, take the square root of both sides, subtract 4, multiply by a -100, and you end up with t equals 400 pi minutes. So that means it takes 400 pi minutes to empty the tank. And then the last thing you're going to do is make a sentence to explain all of this. And I'll let you guys do that. You're going to explain what this is, and then you're going to explain what this is. Alright, so this was a very long problem dealing with antiderivatives, relating it back to related rates. So you can see that calculus never forgets about its old chapters. Okay? Alright, moving on to slope fields. This is going to be a little bit tricky. Okay? Now tomorrow when we start this, you'll see it's not really hard, but you do have to think of a few things. So imagine that the coordinate plane in all points x, y. Suppose that the derivative is equal to f of xy. Is a differential equation, and that the value of dy dx is calculated at every point. And remember, when you find the derivative, what are you finding? You're finding the slope. So basically this is saying, and imagine that the slope is calculated at every point in the plane, and that a tiny line segment is drawn at each point with that slope that we solved for. The resulting set of tiny line segments is called a slope field, and it is sketched with a general solution to a differential equation. Knowing the slopes of the solution to a differential equation at a field of points gives information as to how the solution functions are behaving near given points, and helps us visualize the general shape of these curves. So here's the definition. And this is a plot of short line segments with slopes. Slope fields allow us to graph solutions and curves without having to solve differential equations analytically, which is what we just did in the previous example. And slope fields can also be used to check that we have solved an initial value problem, which is like what we just did in the previous example, correctly. So here's our first example. And honestly, I'm just going to do this, and then we'll do the rest in class together. So we're going to draw the slope field for the differential equation dy dx equals xy. Okay? At each point, xy, where x and y are these integers. So at each point, for x being -1 to 1 and -1 to y. So, and then the initial condition is y of 0 is -1. We'll talk about that in just a second. So here's basically what's happening. What's going to happen? You're going to have your x and your y. But you have to take into account all points possible. You have to match everybody up. So if x is -1, y is going to be -1. But you can also have a -1x and y is 0. You can also have a -1x and y is 1. So you see what we're doing here? We have to plug everyone together. Okay? Now second, when x is the next point over, which is 0, there's also 3 different possibilities. You have -1, 0, and 1, all for x being 0. And then the last part is when x is 1, again, at 1 can be with -1, 1 can be with 0, 1 can be with 1 for the y values. So they gave us the x's and the y's, but we have to make sure that we are plotting every single point. So if you're thinking about it in terms of graphs, our graph is going to be from -1, here's 0, to 1, and from -1 to 1, but we care about every single point in this area. So we want to know at this point, 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 this point, this point, this point, and this point. We want to know the slopes of that equation at all 9 of these points. So what you do is you have your dy dx. It tells you that the slope of x over y is this. So -1 over 1 is 1. And you know that a slope of 1, you have to kind of get good at drawing these slope lines. So we know that a 0 slope looks like this, right? And we know that an undefined slope looks like this. So a +1 slope probably looks like this. And a -1 slope looks like this. Your goal is that if your slope is to change, like if it's +2, you have to make it a little bit more inclined. And if it's -1, again, make it a little bit more steep. So here, -1 divided by 0, undefined. -1 divided by 1, -1. 0 divided by negative 1. So see, I'm just plugging it into that equation. 0 divided by negative 1 is 0. 0 divided by 0, undefined. 0 divided by 1 is 0. 1 divided by negative 1, negative 1. 1 divided by 0, undefined. 1 divided by 1 is 1. So now that I have all of my slopes, these are the slopes at these points, I'm going to graph them. So we're going to start with when x is negative 1. So when x is negative 1 and y is negative 1, my slope was 1. Sorry. When x is negative 1 and y is negative 1, my slope was 1. At negative 1, 0, it's undefined, which means that it goes straight up and down. Here, please cross this out. It should be this way, because at negative 1, 1 is negative 1. Alright, at 0, negative 1, so starting down here, it's 0. At 0, 0, it's undefined. At 0, 1, it's 0. So again, starting at 1, negative 1, it's negative 1. At 1, 0, it's undefined again. And at 1, 1, it's 1. It's positive. So you can kind of see where this graph, what it's telling us. This is telling us that our graph kind of looks like this. This area is all undefined. And then this area kind of does one of these. So slope fields allow us to graph a solution curve without having to integrate it. Okay, so there's my graph without actually having to integrate it. So remember, these are lines of slope for the function. Now, antiderivatives and indefinite integrals. So definition, the set of all antiderivatives of a function f of x is the indefinite integral of f with respect to x is denoted by this. So we all know that. This is nothing new. So when we have found f of x plus c, we have integrated f or evaluated the integral. But we still don't know what c is. So c can be really any point. Alright, so I'm going to set you guys up for this, and then if you can figure it out, it is actually an example in the textbook. So I would recommend that you look at the textbook and try to figure out what it's saying. But basically what you're going to be doing is you are finding the antiderivative, because remember, if you multiply both sides by dx, this is really saying dy is equal to cosine of x dx. So this is telling you that the derivative is this. So what is the antiderivative? So what is y? And the antiderivative of cosine is going to be sine of x plus c. Now the question is, what is that c and how does it impact us? Okay, and you guys can use the textbook to figure it out. Extremely important now that you remember all of these. Okay, you have to remember all of these derivatives and all of the integrals. If you know the derivatives, you should know the integrals. And if you know the integrals, you should know the derivatives. And you're going to have a YARF on this very soon. Alright, I'm not going to go through all of these problems, but you guys know how to integrate. We've been integrating with definite integrals. So here we're going to integrate with indefinite integrals. So basically this is 5x minus 6x squared divided by 2 plus c. Clean it up, you get 5x minus 3x squared plus c. See, at this point, if you forget that plus c, then you're kind of screwed. Okay, you can't forget the plus c in an indefinite integral. Alright, these will be easy if you remembered that the integral of cosine of x tangent of x is cosecant, or negative cosecant. So remember, you take out the coefficient, and then the integral of this is negative cosecant of x plus c. The two negatives cancel out. Alright, so take time to finish these up. They're really easy if you use if you memorize your trig, your derivative and integral rules. Now for this one, the trick is to distribute first. Because if you don't distribute, this looks like a multiplication problem and it looks complicated, but it's really not. Okay? And then for this one, you may want to separate into two integrals. Alright guys, good luck. Enjoy. Yarf is coming.